Welcome back to the next video of energy. In this one, we're going to talk about temperature. Now, the first thing that's really important that you understand is temperature is not the same thing as heat. It's not the same thing as heat, where heat is kind of referring to the total amount of energy in a substance. Temperature is really just referring to the average kinetic energy or the speed of the particles in the object, right? So it's kind of, simple. Cold things have slow-moving particles. Hot things have fast-moving particles. And because of this, you can say a 700-gram substance at 90 degrees Celsius has the same, that's a weird M, same kinetic energy as a 5-gram sample at, that was gross, at 90 degrees Celsius. So two objects can have completely different masses, but as long as they're at the same temperature, their average kinetic energy will be the same. Again, the key here is that it's an average. It's not total. Later, when we talk more about heat and we start talking calculations of heat, the mass plays a big factor. But for now, temperature is simply the speed of the particles in an object. Now, within our temperature section, we could talk about melting points and boiling points. This should not be new information to you, right? Melting point is the point at which something goes from a solid to a liquid. The boiling point of a substance is when the liquid turns into a gas. And we can use these temperatures to determine elements' phases at standard temperature and pressure. Right? So when we're at standard temperature and pressure, we're dealing with 273 K. So for fluorine, we're dealing with a melting point of 53, and we're dealing with a boiling point of 85. These values come from table S on the reference table, right underneath the melting point and the boiling point sections. So here's the skill. The skill is, here is the current temperature. So we ask ourselves, if that is the temperature, have we passed the melting point? 273 is above 53, so we passed the melting point. This substance, fluorine, has melted at 273. Have we also passed the boiling point? Yes, we have also passed the boiling point, because at 85 K, it would have boiled. The temperature is 273, well above it. That makes this substance both melted and boiled. It would be a gas. For chlorine, it's pretty much the same thing. It's just that it's 172 and 239. Yes. So they're higher melting points and higher boiling points, but still, when the temperature is 273, the boiling point has been passed, meaning the substance has boiled, and this is also a gas. For bromine, we're dealing with 266. So even though 266 is very close to 273, at a temperature of 273, this substance would have melted. However, it doesn't boil until the temperature reaches 332 K. And if the temperature is 273, it has passed the melting point. But for this bromine, 273 has not passed the boiling point. It would make this substance a liquid. And lastly, we could deal with iodine, which has a melting point of 387 and a boiling point of 457. And in this case, if the temperature is 273, it falls below our melting point, meaning this substance has never even melted. And what substance has not melted? A solid. So that's how we can use this information on our reference table to determine the phase of all the elements using their melting, boiling points, and the temperature that's given. In this section, we can also talk about the two different scales that the Regents discusses: Celsius scale and Kelvin scale. So Celsius scale was pretty much designed with water in mind, right? 0 degrees being the temperature at which water freezes, 100 degrees being the temperature at which water boils. On this scale, there is the ability to go negative, right? There's such thing as minus 10 degrees Celsius. Kelvin, on the other hand, this scale was designed, right? This scale was designed to stop at 0. 0K is called absolute zero. You can't go any colder than 0K. 0K signifies the temperature at which no thermal energy exists. It's the coldest possible temperature. And it stops at 0. So the big difference between Kelvin and Celsius is that for Celsius you can go negative, for Kelvin you can't. The key is they are scaled exactly the same, whereas every 1 degree Celsius is equal to 1 Kelvin. So their change in value, 10 to 20 C, right, is a 10 Celsius difference. Well, it's also going to be a 10 Kelvin difference as well. So the scaling is the same, it's just their starting points are different. So the conversion is right here. It's also listed on the back of your reference table, right? Table T. Table T has this right here, and it's a very simple addition, subtraction, algebra formula. K equals C plus 273. So all we need to do is take the value that we have and plug it in. For this one, K is equal to 263 plus 273. For the next one, we're also given Celsius as well. So when we're given Celsius, we plug Celsius value into the Celsius part of the equation. This equals minus 252 plus 273. The key there is that we are just plugging the unit that we have in the place of the equation that it belongs. So when we do this, the first one is 536K, and the second one is 21K. So that's going from Celsius to Kelvin. On the flip side, we're going to be kind of working a little backwards. So we have 534K this time. So where do we plug this value? We plug it in the section of the formula that's associated with K. 534 will give me C plus 273. 0K. 0K equals C plus 273. And then you can do algebra or math however you want. For me, I just solve as if this were X. as if this were x. Let me erase that and rewrite that for you so it's not confusing. Right? Solve for this as if it were x. And how do we do that? Subtract 273, subtract 273, subtract 273, subtract 273, and then we just do math, right? And we just do math. So the bottom one, simple, 0 minus 273, minus 273. And for the top one, we're taking 534 and subtracting 273 away from that, leaving us with 261. See. Okay, so that is temperature and how we can convert from one another, how we can use it to solve for the phase of an element. And coming up next, there's going to be some heat calculations. And make sure you like this video, share it, subscribe, and we'll catch you in the next video.